Hello everyone, my name is Caroline Bourdet and I'm presenting topic 11, experimental evaluation on deepfake detection using deepfake recognition, based on the 2021 paper by Ramachandran, Nedim and Ratani, published at the International Carnarvon Conference on Security Technology. I would like to begin with a question. If someone showed you a video of a political figure saying something they never said, how would you know it was fake? Your eyes might not be able to tell, but a biometric system might. That is what this project is about. Here is how the presentation is structured. We will cover the motivation, background on the technology, our methodology, 3 experiments and the results, a discussion comparing our findings to the paper, and a conclusion. I'll then open the notebook briefly to show the code running live. The through line connecting all of this is a single idea. Deepfake detection is a biometric identity problem, not an image classification problem. Let me start why this matters. 96% of deepfakes online target women. The number of deepfake videos has increased by over 900% since 2019. Projected cybercrime losses from deepfake-enabled fraud are estimated at $25 billion by 2027. But beyond the statistics, the specific threat to biometrics is this. Deepfakes are increasingly being used to bypass facial recognition systems, banking apps that verify identity through a selfie, border control systems that match a traveler to their passport, corporate authentication systems. All of these are potentially vulnerable if the face being verified has been fabricated. The question is, how do we detect them? Traditional deepfake detectors approach this as a classification problem. You train a neural network on real and fake images, and it learns to spot the visual artifacts introduced by the generation process. Unnatural blurring around the hairline, inconsistent lighting, texture anomalies. The fundamental weakness of this approach is that it depends on knowing what current deepfakes look like. As the generation quality improves, those artifacts disappear and the detector fails. The biometric approach is fundamentally different. Instead of asking, does this face look fake, we ask, does this face match who it claims to be? We use a pre-trained face recognition system to compare a test image against a known genuine reference. If the identity does not match, the face is fake, regardless of how convincing it looks visually. This is the core insight of Ramachandran et al. 2021, and it is what our entire system is built on. The face recognition model we use is called ArcFace, proposed by Deng et al. In 2019 at CVPR. ArcFace uses a RustNet50 backbone, a deep convolutional neural network with 50 layers. Given a face image, it outputs a 512-dimensional embedding vector. You can think of this as a numerical identity fingerprint, 512 numbers that uniquely characterize a person's facial structure. What makes ArcFace particularly well suited for this task is its loss function. Standard face recognition uses softmax loss, which simply learns to classify identities. And ArcFace uses an additive angular margin loss, which explicitly maximizes the angular separation between different identities in embedding space. This means different people's embeddings are pushed as far apart as possible, making comparisons more discriminative. Now, why does this detect deepfakes? So face swapping algorithms replace the visual appearance of one face with another at the pixel level. These are very good at making the result look convincing, but they cannot replicate the subtle structural identity cues that ArcFace encodes. The precise geometric relationships between facial landmarks, sub-pixel skin texture patterns, and microstructural features unique to each person. The blending operation corrupts these cues, and the resulting embedding no longer matches the genuine reference. An analogy we can use is a very convincing mask of someone's face would fool a casual observer, but a fingerprint scanner would immediately detect it because it measures something the mask cannot replicate. ArcFace is the fingerprint scanner for faces. Our detection pipeline has 4 steps. First, we load a reference image, a known genuine photo of the target identity. Second, we load the test image, the image we want to classify as a real or fake. Third, we extract ArcFace embeddings from both images using the Deepfake detection Python library. Fourth, we compute the cosine similarity between the 2 embeddings and compare it against a threshold of 0.60. Cosine similarity measures the angle between 2 vectors in 512 dimensional space. A score of 1.0 means the vector point in exactly the same direction, same identity. A score near 0 means they are perpendicular, different identities. We choose 0.60 as our threshold because it accommodates natural variation in real-world photos while maintaining 0 false positives on our test data. The 2 lines of code at the bottom of this slide are the entire detection decision. Extract embeddings, compute similarity, classify. That is the complete system. So we conducted 3 experiments using 3 different data sets. The first used a small manually collected set, photos of Barack Obama as the reference identity with photos of Biden, Bush, and Powell as imposter tests. This was designed to demonstrate the basic concept. The second dataset used the labeled faces in the wild dataset, LFW, the standard benchmark for face verification research, originally published by Huang et al. At ECCV workshop in 2007. We selected the 5 subjects with the most photographs: George W. Bush, Colin Powell, Tony Blair, and Donald Rumsfeld, and Gerard Schroeder, and constructed 135 test pairs, which is 75 genuine and 60 imposter. The third and most important used FaceForensics++, the large-scale deepfake video dataset published by Rossler et al. At ICCV in 2019. We downloaded 10 FaceSwaps deepfake videos and 10 corresponding original videos at compression level C40, which is the most compressed level and the most realistic scenario, extracting 5 frames per video for a total of 50 real versus deepfake pairs. So now for results. Here were our results across all 3 experiments. The small-scale demonstration produced 6 out of 6 correct classification. Genuine pairs, so Obama versus Obama, scored 0.6495 and 0.6379. For the imposter pairs, we had Obama versus Biden, Obama versus Bush, Obama versus Powell, and those scored between 0.0097 and 0.2519. And we can see that the separation is really striking. For the LFW evaluation, it produced a false positive rate of exactly 0 at our operating threshold. No imposter was ever accepted as genuine, with a true positive rate of 86.7%. And for the last one, the FaceForensics++ deepfake detection produced 100% accuracy. All 50 deepfake pairs correctly classified as fake, with a mean score of 0.280 and a maximum score of 531, which is still safely below our threshold of 0.60. This combined score distribution plot is the visual centerpiece of the project. The green histograms represent 75 genuine pairs from LFW, so same person, different photos. They cluster between 0.30 and 1.0 with a mean of 0.52. The orange histogram represents 60 LFW imposter pairs, so different people, tightly clustered between negative 0.60 and 0.34 with a mean of 0.12. The red histogram represents our 50 FaceForensics deepfake pairs with a mean of 0.28. The dashed line you see at 0.60 cleanly separates genuine pairs from both imposters and deepfakes. We can see that no imposter or deepfake scored above the threshold, which is great. One important observation here is that deepfake scores higher than random imposters, so 0.28 versus 0.12. And this is expected. A face swap deepfake of a person A retains that person's hair, skin tone, and overall face shape, which contributes partial identity signal. Deepfakes are harder to reject than completely different people, but our threshold still catches all of them. The ROC curve, receiving operating characteristic curve, plots the true positive rate against the false positive rate across all possible thresholds. A perfect classifier reaches the top left corner. A random classifier follows the diagonal. The area under the curve, or AUC, summarizes overall performance in a single number. An AUC of 1.0 is perfect. An AUC of 0.5 is no better than random guessing. Our AUC of 0.918 means the system correctly ranks a genuine pair above an imposter pair 91.8% of the time across all thresholds. The red dot marks our operating point at threshold 0.60, true positive rate of 0.867, and a false positive rate of 0. Our area under the curve is below the paper's 0.98, which is expected. The paper evaluates deepfake detection on celeb DF, where identity mismatches are more pronounced. We evaluate on unconstrained real-world photos with large natural variation in lighting, age, and pose, which is a fundamentally hard task. So here are the actual FaceForensics detection results. Each pair shows the real reference on the left, the real reference frame on the left, and the FaceSwap deepfake on the right, with the cosine similarity score and the system's decision. So looking at the first row, person 183 is shown in a real video frame. In the deepfake version, person 253's face has been swapped onto person's 183's body. The system scores this at 0.123, far below threshold, and correctly classifies it as fake. What is notable here is that this detection does not depend on the deepfake looking bad. Some of these deepfakes look visually plausible. The detection relies on the deepfake failing to match the identity of the reference person at a deep feature level that the face swapping algorithm simply cannot replicate. Comparing our results to the paper, Ramachandran et al. Report area under the curve of 0.98 and EER of 7.1% on CelebDF using ArcFace with cost-face loss. And that outperforms CNN-based detectors by approximately 20%. Our FaceForensic accuracy of 100% matches or exceeds some of the paper's per method results. our LFW AUC of 0.918 reflects the harder evaluation task. So, the strength of this biometric approach, of this biometric approach are significant. No deepfake training data required, generalization to any new deepfake method, 0 false positives, and an interpretable confidence score. The limitations are equally worth acknowledging. The approach requires a genuine reference image of the target identity. Expression swap methods like face-to-face and neural textures, which modify only facial expressions while preserving identity, are much harder to detect. The paper reports error rates of 30 to 50% for those methods, and 13.3% of genuine pairs in our LFW evaluation fell below the threshold due to large natural variation between photos of the same person. To conclude, this project demonstrates that biometric face recognition is a powerful and generalizable approach to deepfake detection, one that requires no deepfake training data whatsoever. Our system achieves 100% detection accuracy on FaceForensics FaceSwap deepfakes and an area under the curve of 0.918 on LFW face verification, confirming that the core finding of Ramachandran et al. 2021. The key takeaway is this. As deepfake generation continues to improve and visual artifacts become increasingly difficult to detect, approaches grounded in biometric identity will likely become more important, not less. A system that measures who a face claims to be, rather than how convincing it looks, is inherently more robust to advances in generation quality. Thank you for your attention. So, now let me open the notebook to show the code running. Okay. So here in step 4, you can see the cosine similarity. Obama versus Obama score is 0.6495, genuine. And Obama versus Biden score is 0.0097, fake. The margin is enormous. Now in in step 5, yeah. In step 5, we have all 6 detection test runs. And you can see each decision printed with the similarity score and the margin from threshold. Yeah, so that's 6 out of 6 correct. That's great. Now let's go to step 9B. Okay, so here in step 9B, we can see the FaceForensics results. So we have 50 pairs and 50 correctly detected as fake with 0 failures and a mean score of 0.280. And this complete notebook and all code are available on GitHub, and there's going to be a 5-minute demo video that goes more in depth about it. I'm happy to take any questions in the comments. Thank you for your time.